So it relates to this debate of dynamics first versus geometry first, right? That
Right.
what is more fundamental, dynamics or geometry? And if I'm
Mhm.
not wrong, I think you go towards the dynamics first view, right?
That's correct.
So
Yeah.
so can you tell us a bit about that project, and can you also tell us that what is space time if it is not something, if it is not reflecting something metaphysically substantiative?
Right. So I wouldn't say it's not reflecting something metaphysically substantial, um, but that something that it's reflecting is more of a structural feature of the world as a whole, rather than um, like a stage on which the players, dance around in the old like Newtonian vision of the world. Right. But it's a very big topic. I mean, I wrote my whole PhD thesis on it. So where to begin?
I mean, you can start by explaining what is dynamics first versus geometry first debate.
Right, right. Yeah, so that's a debate which is very popular in Oxford. There's lots of people discussing it there, which is how I got introduced to it. Um, but the question is essentially, um, well, let's think about special relativity to start with. You have, of course, this Lorentzian metric that you write down whenever you're writing down the theory. But is that a real geometric feature of space-time, in the sense that you can imagine building up the world one step at a time? First, you have like maybe a topological setting, just the topology of R4, and then God comes along and he puts a metric structure on it that it just has intrinsically. So the space-time manifold, independent of what goes on it at a later point, has certain geometric qualities to it. This is the geometry first view. And then God comes along and sprinkles the fields and particles and everything on it. And they have their own symmetry groups, the Poincare symmetry of their equations. But that, because of the setting that they're on, has to match the geometry. So it's the symmetry of the geometry which first and foremost fixes the geometry or the symmetry of the matter that goes on the spacetime. And so you have this idea that the symmetries of the geometric structure is somehow constraining the symmetries of the dynamical laws, that there's somehow derivative or come later, or the particles can only behave in the paths and grooves carved into the space-time already, something like that. So that's the geometry first view, and I think that's very intuitive for a lot of people, the way general relativity or special relativity we're talking about is set up. But there's another way to think about it, where um, when we say that the space-time manifold has its certain geometric structure, the only reason it has this, argue the dynamics first camp, is because the dynamics of matter is such and such. So there's no fixed geometric facts about lengths and distances, proper times and such, that then our uh, rods and clocks have dynamics such that they measure that pre-existing geometric structure. The geometric structure of the world is entirely exhausted by the fact that our dynamics do have this Poincare symmetry, and thereby the spacetime has its Lorentzian structure. So the question is whether it's the geometry of the world dictating or governing how the dynamics might behave, or if just a dynamical description of how the things we call rods and clocks behave, if that is the full story for what there is in terms of geometry.
So if you lean towards the dynamics first view, someone may come along and say that, well, in cosmology, right, when they solve Einstein's field
Mm.
equations, you can have solutions of Einstein field equations where there is no matter and there is no
Mhm.
cosmological constant. So there is no matter. There are some solutions where there is no matter, only space and time. So how would you make sense
Right.
of that?
Right. Yeah. So that's a bit of a puzzle, which has been raised before, and there's basically, well, there's at least two ways I think of as being reasonable to go here. Either you bite the bullet and say that, well, when we attribute geometry to those solutions, or we shouldn't, that they actually have no geometric structure. But a little more subtle way to say that is that we reason about those through analogy. When we say they have some geometric structure, what are you going to articulate that in terms of? There's no stuff in there doing that, but you would put in test particles and you would notice the test particles moving along this. So it's kind of counterfactually, there's that empty universe, but nearby to it is a universe with a test particle and it moves in such a way, or something. So it's by these kind of counterfactual nearby possibilities of test particles existing that we say, if there was a measurement device here to measure something, then it would get this result. And in that sense, the empty universe also has that property, although literally speaking, it doesn't have a measurement device in it. So you can kind of argue counterfactually that um,
Right.
that's how that those empty spacetimes get their geometric structure. Yeah.
So how should we think about, those solutions of Einstein field equations? We should think that they have no geometry unless there is some matter to measure it.
Right, right. Well, if later on we bring QFT into the picture, there is really no such thing as an empty spacetime. So another
Hmm.
way to go is just to say these empty versions of spacetime are they appear in the model, but we shouldn't take them physically seriously because we know that QFTs are what the world is actually full of, and those have non-zero expectations of or variances of energy throughout the field. So another way to go is just to deny that we should be trying to take those models seriously. They might be useful for modeling and practical purposes, but as a literal description of a possible universe, we might reject them.
So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.